Okay, we look at the problem sheet number 9, and I've given some model answers. Let me run through that with you. Okay, the first question is that you've been given a signal xn, and the spectral information is given to you, and is upsampled by 3. You get Wm, then you have got a filter, and the filter is a pass band, is a low pass filter with a cutoff frequency of pi over 3 and a gain factor of 1 it has got, and then you downsample by 2 and you need to draw the spectrum. So we can start with first original one. So this is your xn in here, and first time the first block is upsampling by 3. So what happened is this is now multiplied by the 3 is like the whole thing is divided by 3, so that will come as 2 pi over 9, that position. So when you say you're upsampling by 3, 3 of these should be between pi and minus pi. So we've got 1, 2, 3. So that's your first step. Then we look at the filter. The filter has got a bandwidth, is a bandwidth of pi over 3. So the filter, if you draw that on top of this, it's like that. It's bandwidth of pi over, sorry, it's in here. So what will happen is the filter will take out, when you apply the filter to this, this will be gone and that will be gone. So you are left with only that one. So when you are upsampling, the gain does not change. That's another part that you need to look at it. And then you are downsampling by 2. That means this gain is now divided by 2, which gives you 1 over 2. And then you multiply the it's 2 pi over, this is 2 pi over 9. So if you multiply this position by 2, you get that position comes to 2 pi over 3. And that position is now, that position will be 2 pi over 3. So spectrum stretches when you downsample by 2, and that the gain is reduced by half, and spectrum stretches, so pi over 3 multiplied by 2 will become 2 pi over 3 here, and that's that part, and the same thing here. So it's just spectrum stretched. So that's a kind of an easy exercise where you've got a spectrum given, and then you compress it first, filter it to remove the other 2, and then stretch it. Okay? And look at this question. The signal that you have is 44 kilohertz at this position, and what you want here is 16 kilohertz. So how do you achieve this one? So you could start with 44 L over M is equal to 16. Therefore L is the upsampling, M is the downsampling part. 4 upsample, downsample by 11. So you take the signal 44 here and upsample 4, it will become 176. So this filter will be operating at 176 kilohertz, and then you downsample by 11, and that will give you 16 kilohertz. So that's exactly what you're going to do. And the bandwidth of this filter depends on the sampling. This is 16 kilohertz, so you must have 3 dB bandwidth, 8 kilohertz, half the sampling of that. So it says the 8 kilohertz required for the cutoff frequency of the low pass filter. So that's another example. And the next question is, what sort of filter will you use here? Will you use an IAR filter, or will you use an FIR filter? That's the question. Now if you use an IAR filter, have a look here. Current output depends on past inputs and also past outputs. That means here you're going to calculate, if this is an IAR filter, if you have say here like 1000 samples coming in, you must have 1000 samples here, then you drop out you keep every 11 sample. So you must calculate all the 1000 samples before you dropping out, before you throw out the samples. Because current output depends on past input plus past output. So every sample output is required to calculate the next output. But if you use FIR filter here instead of IAR filter, now so if you look at FIR filter, so what happened in the FIR case, your current output, what's here, depends only the current input and past inputs. So if you have 1000 samples here, naturally you would have 1000 here, but you don't need to calculate all the 1000 because you're saying you have to downsample by 11, mean you calculate the first one, 11 sample out, and calculate the next one, 11 out, then the next one. So you only have to calculate the samples that you needed. And in order to calculate this doesn't depend on the previous outputs, because previous outputs are not required. This calculation depends on only previous input, not the previous output. Therefore, the computational rate here, you don't need to calculate every sample and then throw it out. You just calculate the sample that you require if you use FIR filter. So we tend to use FIR filter here. Do you understand that part? IAR filter, to calculate this one, you must know these values. To calculate this one, you must know these values. But for FIR filter, you calculate that one and that one. To calculate that one, you don't need these values at all. Not all of them, the previous two of them. Okay. Another reason for FIR filter is that linear phase filter can be designed very easily. That is, one of the attraction of FIR filter. But having said that, FIR filter needs larger number of coefficients. That's one of the higher filter orders required compared to IAR filter. So you need to compromise. You need to say, look, I'm not interested in linear phase. I'm not interested in speed. In that case, just use a simple IAR filter here. Will do the job for you. Okay? But you will find in almost all the application FIR filters preferred for linear phase reasons, and also implementation is, I wouldn't say implementation is simple, but linear phase is the main reason. And also computation is, you don't need to calculate all the samples, you only calculate the required samples. And in question 3a, have a look, you've been given a system here. It's a system with the modulation. And the input signal is HK. You've been asked to find the impulse response of the system shown for the kth channel. So the overall impulse responses you need to show is that H1n is the impulse response of this one and that one. So this is a kth channel. There are many channels there. One channel is called kth channel. So this is our kth channel. So how do you do this question? Very easy. So you want impulse response, so you give delta n here. And you calculate delta n, go through this path and have it. And then you calculate delta n going through this path and calculate and add them, you get the output. So let's start with this one. So what do we do? So we start one step at a time in this question, and we'll take you through that. So I want to calculate x1n. So what is x1n? x1n is at that position, which is delta n multiplied by cosine theta k. So x1n cosine theta k is delta n multiplied by cosine theta k. So cos n is that delta n is at that position. So when you multiply this and this position, it will be 1. All the other position delta is 0. Therefore, all the others multiplication is 0. So all you will get is, when I say is 1 means delta n. That's what you will get when you multiply. Because cos at 0 is 1. 1 times the delta n is delta n. And if you calculate x to n, which is x1 delta n multiplied by sine, x to n is xn multiplied by sine, which is delta n sine. If you look at the sine curve, sine is that way. So that is 0 sine value at that position. So that multiplied by that will be 0. That's gone. And that is 0 and multiply 0, 0. And everything is 0 when you multiply them for the sine. So, and sine at theta equals 0 is 0. And delta is 1. But 0 times 1 is 0. So that's 0. So that's, you get 0 here. Here you will get delta n. Now if you take y1n, which is here, which is x1n, this one, convolved with h1n. And x1n is delta, he showed it there. If you convolve with delta n with the xn, always you get that back. Anything you impulse function, if you convolve with this, always you get this back, because impulse will not distort. And if you take y to n, basically this one convolve with that one, but this is already 0, therefore y2 will be 0. So if this is 0 and this is 0, so this is not going to contribute anything, so anything coming through is the answer. So what you will have is ykn will be equal to y1n, that is that one we have calculated, multiplied by cos kn. y1n we calculated just now as h1n, so it becomes h1n cos n theta. That's what you are asked to prove in the first part. So it's only one channel is effective here. The channel that's effective here is the upper channel, upper part. So this part is contributing to you, and this one is because this 0 is not working out. That's all that question part is. Now we move on to the next part of this question. The same question. You've been asked to show the frequency response h theta k is given by that. So knowing y and k is that, and what is h theta k is our Fourier transform or discrete signal. So that is hkn multiply e to the j theta n. Hkn is our, this is the output, so that's yn, that's that exactly same, which is exactly same as that. Because all we are trying to find out what is h theta here. So you are going to use this signal to do the calculation. So that signal is here and that signal is the same thing. So h theta, hk theta is equal to that one. Okay. Now the next step is we replace this one by our e to the j theta nk, which you have done many times, and it's divided by 2. Right? Cos is, so you start with e to the j theta is equal to cos theta plus j sin theta, and e to the minus j theta is equal to cos theta minus j sin theta, and add them, you'll get this part, this one. So now what we need to do, you can now combine that one with that and that one with that. So you separate them. So you get h theta k is equal to, take the half out, h1n multiplied by these two combined, that's that one. Sorry, that one and that one combined. And then you combine this and this, same summation for both of them. This is a summation of a plus b is summation of a plus summation of b. Yeah? So that's what we are doing here. So one is this one is that one. Now if you go back and look at your definition of discrete time Fourier transform, or discrete time Fourier transform, this is equal to h, whatever shift here, which is h theta minus theta k, and the half will be there. This is equal to h theta plus theta k, that's there, and the half will be there. That's all the proof is hk. So basically what you have done here is, if you go back and relook it again, what you've basically done is this is given, you need to find h theta k, which is like yk theta. It's the same thing. So we go and look at our formula for discrete time Fourier transform, and which is hk, that's hk, the inverse of it, and e to the j theta, which is exactly yk e to the j theta, which is exactly that much is the output. So this is replaced by that. And then you just simply used your simple mathematics to prove that. Okay, straightforward. Next part is, if xn is this, you've been given x is a cosine function, then using the figure, and the output signal ykn is essentially the input signal. We are going to show that and that are identical. Right? Essentially means it could be scaled, it could be, normally it has to be spelled out, but what's I say, essentially identical mean it will be, if this is cosine theta, the output also has to be cosine theta naught, but it could be half or 3 or whatever. Okay, let's start with x1 at that position, that multiplied by the original. x1 is that multiplied by the original. And you use trigonometry here. It is, you will have cos A times cos B formula, which is like, should be 2 cos A, but it's half cos A minus B times cos A plus B. That's the trigonometry formula. That formula will be given if that question is there in the exam or anywhere. Normally you are not expected to remember that. It will be given. Similarly, x2, take the input, multiply by sine, so which is that. Again, that's the trigonometry formula. That will have a negative sign according to the formula, half, then that minus that, that is that, and that plus that is that. They are the two values there. Now, we are going to assume nothing is mentioned about this filter, which they should have given you. This filter is a narrow band filter, and if you look at that spectrum, you're going to have one spectrum theta naught minus theta k. So if you say theta k is here, theta naught minus theta k is this. This is theta naught. And the other one is theta naught plus theta k, which is here. That's the second one there. This is theta naught plus theta k. This is theta naught minus theta k, and that's frequency axis. If you assume that this filter is a narrow band filter, right? This is the filter, which means the filter is such that it will only allow this part. This is gone. Only that comes through. Now, from the question, it's not clear actually. It's not given really. This step is missing in the question. Normally, it will be mentioned that it's a narrow band low pass filter, which can only pass that frequency. So you remove this one, and when you remove that, what will happen is, you remove this one, this is gone in both cases. Those two are, because there are two filters. So you will end up with, at y1 will be only this part, half cos theta, okay, and y2, which is here, which will be only that one, because the filter removes them. Now what you are doing is, now you are multiplying this and this one, so you take ykn, this one equal to these two multiplied and these two multiplied, and add them. So we could say that is y1 cosine theta k, y1 cosine theta k, that's at that point, y2 sine theta k, that's at that point. Add them, both of them. So that's what you're doing now. You are adding both of them. When you add them, after multiply and add them, what would you get basically? So y1 multiplied by that is this, y2 multiplied by that is that. We already know y1 and y2 and put them in here. So y1 is that, multiplied by that, and then that one. And then if you look at the formula, this look like cos A plus B is cos A cos B minus cos A A sine A, sine B is in that format. So you combine them, you will get this. And now you will find n, when you multiply that, cancel with that, you end up with half cosine theta naught. So input was cosine theta naught, the output is scaled by 2. Now the question you'll ask is then, how do I make it identical? What do I need to do? That's the next part. It's not mentioned here. Well, how do you remove this? So one of the way to remove it, you give a gain to this filter at 2, right? So when it goes through them, you have a gain of 2, that will then cancel them out. That's another way of looking at it. All right, we come to this question now. So for the diagram shown below, which are the right answers? And you know that Wm is not Xn because there's an operation happening. So definitely this is not correct. Vn is not equal to Vm. That's not correct either. And Vn is related to this one, not related to that one by an equation directly. So that's not correct either. So what happened is we know here Wm is equal to x kind of 3n, right? Every third one. And here Vn is equal to Vmo2, right? Mo3. Yeah. So these equations are completely wrong. Therefore, that should be the answer for this. So the answer is B. And let's look at this question. You've got a signal coming at 8 kHz sampling, and it has got a bandwidth of 2 kHz. It will allow 4, but it's only have, so they must have used a filter here to make it 2 kHz bandwidth, 2 kHz. You upsample them, so bandwidth no change. Then you use a digital filter to join the samples. Then you downsample them by 4, you get 14 kHz. So if this is 14 kHz, this should have a filter bandwidth of 7 kHz. That would be the normal. Yeah. But if your original spectrum is only 2 kHz, why do you put a lot of effort to make this 7? So all you need to do, the bandwidth of the filter is 2 would do, like for you, 2 kHz will do. Because no signal outside the 2 kHz is coming through. So all you need a bandwidth of 2 kHz. So the answer for this question will be, what would be the minimum cutoff frequency? Right? 2 would be the minimum. The maximum cutoff frequency would be 7. You can't go anything above 7, it will be aliasing. The bandwidth is only 2 kHz, 0 to 2. Therefore, 2 is the answer for that question. Okay? I think this is another question that in the spectrum, I think there's an error. If you have H1 theta, that H2 theta, that should be H3 theta. And in the notes it was H2, I think. That's wrong. H3 theta. So you've been given H1, you've been given H2, you've been given H3. This is a low pass filter, and this is a band pass filter, and this is the band pass filter. Input spectrum is given like this shape, going through a low pass filter, then down sampled by 4, up sampled by 5, and you find this first. Once you have found that, then you work this channel and that channel separately. And multiplication mean modulation happen here. Okay? So let's go to the next page looking at this question and see how we are doing it. So we are only interested on that at the moment. Xn, x theta, let's plot that. So x theta is given, that's our x theta. Then we plot the low pass filter, which is between pi over 4. So it's between there and dot 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 dot, there, dot dot dot, that. That's our low pass filter. So this spectrum multiplied by the low pass filter spectrum will give you the spectrum at there, which we call u theta. So if you multiply this with this is all zeros, so you will be only keeping that part. That's the only one comes through this. So here is go. That's u theta. That's at that point. That point you have got u theta. The next part is downsample by 4. That means stretch it by 4. So 4 means you go and take this position, multiply that by 4. So pi over 4 multiplied by 4 will give you pi. So that position is now stretched to pi. So you see that position is now here. And you will find that's also stretched, say there. So that's pi and that's pi. Agreed? That's p theta. Now what happens is that you are upsampling by 5 to get q theta. So between pi and this one, you must get 5 of these altogether. That's compression. So you'll find that position comes to pi over 5 because it's down this upsampling by 5, and that position comes by pi over 5. That's your first one. Up to this one, huh? And the first one is from there. Then you got a second one, and you got a third one, and then you got a fourth one, and then you got a fifth one. There should be 5 of them. We learned that before. So q theta has got that spectrum. Now we're going to go through that path and that path, right? So you're clear at the moment what q theta is. Now you go to the next page. So I drew the q theta. Now we take H3. So we're going to take that path now. H3 is a bandpass filter. So the bandwidth is 3 pi over pi, 2 pi over pi. So that's your bandpass filter. Now, and similarly on the negative side also bandpass filter. So bandpass filter will make sure that this spectrum that's gone, and then it'll keep this up to this one. So that's gone, and that part is gone, all gone. Gone up to that, and that's kept. That part is also gone. So all you'll get is bandpass filter only keep that bit and that bit. So you'll find here you are, that bit and that bit. That's your r theta there. And it's ready here now. Now we go and look at this spectrum. Same q theta, which is here. There. Going through a bandpass filter H2 theta. H2 theta is 2 pi over 5, pi over 5. Where is 2 pi over 5, pi over 5? There and there, and that's 0. And when you get that spectrum and then multiply by that, you multiply these two. So it will keep that part, it'll keep that part, and the rest all gone. So what you end up is v theta is that. So at that point you got v theta. Now what happened is v theta, now from here you go here, the v theta I redrawn here, going to be multiplied by 2 pi over 5. So this spectrum, whatever spectrum, is going to be shifted around 2 pi over 5. That's your carrier frequency. So 2 pi over 5 is here, and these two will be centered around, this is at 0, that will become now 2 pi over 5. So when you do that, this part will move there, and this part will move here. Similarly, you'll have a negative one. When you do minus 2 pi over 5, that will move here, there, and that will move here. So you got your spectrum now for S theta. So you got the S theta spectrum. Now what you need to do, once you have got the S theta spectrum, that's this one, you add both of them. You have R theta here. So R theta is that, S theta is this. You add these two together. When you add to them, they are not overlapping. So this one is that much, and this one is that much. When you add them, you will find this fellow is at here. So you'll get that. And then you've got these two added up, so that will be there, and then you'll have that one. This is all between pi and, that's your final spectrum. That's the answer for that question. And remember that, as I said to you, there's a small error in the notebook, that's H3 theta, not H2 theta. If you have tried the question with H2 theta, you'll get a different answer. We come to the last part, simple multiple choice. Which of the following are correct in this case? So interpolation may be used to increase the sound quality of the digital signal. That's not true. Interpolation does not increase. The spectral information is still same. It doesn't improve the quality. Same quality whatever you had. That won't be correct. Spectrum is compressed by upsampling. So that's good. That's correct. That's second one is right. That's correct. Multi-rate signal processing may be used to allow system with the different sampling rates to interpolate. Yeah, that's correct. Multi-rate system in different sampling rates. So that's also correct. Decimation is effective and lossless compression mechanism when employed on a speech signal. That's not a correct answer. You're saying decimation is an effective and lossless compression. No, decimation means you have to use a low pass filter which removes the information. So that is not correct. So basically the answer is 2 and 3. 2 and 3 is the D part. So that will be D. The answer is correct. Okay. Next one, the spectrum x theta corresponds to the digital signal. That's the digital signal passed through a L4 interpolator. Which of the following corresponds to the certain spectrum? So it has to be compression. So that pi over 2 multiplied by 4, right? So it will sorry, not multiply by 4, it's divide by 4. Why multiply 4? It's just only 4. So that position has to go to pi over 8. So where is it happening? Is it happening here? No, that's not correct. It's happening. This is correct. But we come back to that. This is not correct. Pi over 8 here. No, that's not correct either. This is happen. This position has to go to pi over 8. So it's there. Now remember, it's 4. There should be 4 of these in this graph. There should be 4 of these. So only 1 is written. So this answer is not the accurate answer. Having said that, this spectrum will be there. This is correct. So the remaining 4 has to be. There should be another one, which is the one, and then there's there, and there was another one, and there's another one. So 1, 2, 3, that half, 4 will be there. This should have been given in this question. This was not given, but this is the closest answer that you can give. So fundamentally, you need to get this part right, which is pi over 8. So B is the answer for this question. Next question, which of the following are true? It is always suitable to decimate then interpolate when performing a rate conversion non-integer. Is that correct? That's not true. It's not always suitable to decimate. You can't say. There are cases where you've got to always do interpolation first and decimation. So this is not always the case. That's not correct. The second one would be sampling rate conversion enables increasing or decreasing sampling rate. That's the idea behind so that is correct. In general, decimation is not possible without interpolation. Is that correct? It says in general decimation. I don't think this is correct. Decimation is not possible without interpolation first. Now you can do independently without interpolation, just decimation on its own, right? So the next one would be then interpolation, upsampling, low pass filtering is a lossless process. No information is destroyed or distorted. That's correct. When you do the interpolation, it will retain the original information. You are upsampling it, but original bandwidth of the signal will be still retained. So this is correct. So the answer is 2 and 4 are the correct one. So 2 and 4 are that which belongs to C. Okay, I think that's all the chapter is on that one. I hope that you have understood this chapter. Try to do these questions again yourself and see whether you're able to draw the spectrum. Okay, thank you.